All right, team, let's get started. As your powertrain consultant, my job is to give you the blueprint for a winning Formula Student EV. We're going to cut through the noise, avoid the rookie mistakes, and architect a world-class electric race car from the ground up. So let's dive right into the single most misunderstood part of this entire competition.
So let me ask you a question. When you think about a winning race car, what's the first thing that pops into your head? You probably picture a screaming engine, huge horsepower, just pure raw power, right? Well, if that was your answer, I'm here to tell you that in this particular game, that kind of thinking is a one-way ticket to the back of the grid. In Formula Student Electric, raw power isn't king, not even close.
And here's why. 80 kilowatts. Burn this number into your brain. It is the single most important rule that shapes our entire design. You see, every single car out there is capped at exactly 80 kilowatts of power. It's the great equalizer. It means you can't just throw a bigger motor at the problem. You can't win with brute force. You have to win by being smart.
So if everybody is playing with the same power limit, the entire battlefield shifts. You don't win races on the straights anymore. You win them in the braking zones and through the corners. The new winning formula? It all boils down to two things: just relentless energy efficiency and pushing the absolute ragged edge of dynamic control.
And that brings us right to the heart of our project. This is our secret weapon, our competitive advantage, the energy management system. You'll hear us call it the EMS. And listen, this is not just another box of electronics. This is the car's central nervous system. It's the brain making every single decision out there on the track.
Let's be really clear about what the EMS does. It's the electronic brain that's constantly taking in data, what the driver's doing, what the wheels are doing, how the battery is feeling, and it intelligently decides exactly how much torque to send to the motors at any given millisecond. The goal is simple: squeeze every last drop of performance out of the energy you have, all while staying under that 80 kilowatt ceiling.
Now, to tackle a system this complex, we're not just going to start coding blindly. We're going to use a professional McKinsey-style approach called the MISI principle. It just means we're going to break this big problem down into two smaller, distinct subsystems that together cover everything we need to do. Basically, how we save energy and how we use that energy to go faster.
The whole architecture is pretty straightforward when you look at it like this. Just think of it like a person. The inputs are the car's senses, right? Pedal positions, wheel speeds, battery voltage. The EMS itself is the brain, running all this data through its logic to figure out what's happening and what to do next. And the outputs, those are the commands, the precise torque request it sends out to the muscles, in our case, the motors. It's a constant loop: sense, think, act, repeat, hundreds of times a second.
Okay, let's jump into our first subsystem. And believe me, this one is a total game changer. We're talking about regenerative braking. Now, this isn't some gimmick to feel good about being green. In our world, this is a weapon. It turns wasted energy into a real, tangible, strategic advantage.
The potential here is just staggering. In a single 22-kilometer endurance event, a top-tier EMS can recover and literally reuse up to 25% of the total energy you put into the car. Think about that. A quarter of your energy comes back for free. Every braking zone stops being just about slowing down and starts being about refueling for the next straight.
And the strategy here is crystal clear. Every bit of energy you get back is weight you don't have to carry in your battery pack from the start line. Being more efficient lets you build a smaller, lighter battery. And what's the golden rule of racing? A lighter car is a faster car. Period. It changes direction faster, it accelerates harder, it's easier on the tires. That's where you find lap time.
This efficiency creates this incredible ripple effect through the whole car design. By using the motor to do a big chunk of the braking, we take a massive thermal load off the mechanical brakes. We're talking about dropping peak brake disc temperatures by over 20%. That means we can run smaller, lighter calipers and discs, which cuts down on our unsprung mass, and that's absolutely critical for how the car handles.
All right, on to our second subsystem. If regenerative braking was all about saving energy, this part is about using it with absolute surgical precision. This is where we get into ultimate vehicle dynamics. This is where we create a massive performance gap between us and our competition.
So to understand this, you first have to understand a concept called slip ratio. It's actually a pretty simple idea, but it has huge implications. You see, a tire doesn't generate its maximum braking force when it's completely locked up and skidding. No way. The most grip happens in this tiny, perfect little window, when the tire is slipping just a little bit, somewhere around 10 to 15%. That knife's edge, that's where peak performance lives.
So the million-dollar question is, how do we stay on that knife's edge? Well, the old-school way was with something called a PID controller, which is purely reactive. But the state-of-the-art, and what you guys are going to build, is called Model Predictive Control, or MPC. Think of MPC like a chess grandmaster. It's not just reacting to the last move. It's predicting what the road surface will be like in the future, and it's constantly calculating the absolute perfect braking torque to keep you right in that sweet spot.
And what's the payoff for all this complex math? How about this? 7.7%. By using MPC to keep those tires at their absolute peak grip, you can shorten your braking distances by a staggering 7.7%. In a sport where you win or lose by thousandths of a second, that is an eternity you gain in every single corner of the track.
Now, you can't just hack together a system this critical and this complex and hope for the best. To make sure it's bulletproof, reliable, and performs exactly as designed, we are going to follow the exact same rigorous development process used by the best automotive and aerospace companies in the world.
We're going to use what's called the V model. It's a simple, incredibly powerful roadmap. First, we build and test everything in a completely virtual simulation. That's model in the loop. Then, we take our physical controller, the actual brain, and we plug it into that simulation to test it against millions of scenarios. That's hardware in the loop. And only when it passes every single virtual test do we earn the right to move to the real car for final validation on the track. No guesswork, just pure, disciplined engineering.
So if you only take one single thing away from this briefing today, please let it be this. In Formula Student Electric, the game has completely changed. The team with the smartest, most efficient, most predictive control system will beat the team with the biggest battery. Every single time. You now have the strategic blueprint for a world-class energy management system. The path forward is clear. So the question I'm going to leave you with is this. How are you going to take this foundation and innovate on top of it to build not just a winning car, but a dominant one? All right, let's get to work.